Okay, so let's look at the second example over here where I have two blocks, 3 kilograms, 2 kilograms, and I'm going to pull it with some external force of, let's say, 10 newtons, and I'm pulling it this way. Okay, and my goal is to find out what's the acceleration of each object, okay, and the whole system. So that's the goal over there, and it's connected by a massless, inextensible rope like this. So the first thing we need to do is draw the free body diagram of everything, and I've drawn for both of these. Let's start with B. So this should be the part that you now become more familiar with, right? So there's an external pull over here. So there's a pull, and there's also it's what's in contact with it. It's in contact with the rope. So there's also a tension on this side, right? So we have a specific name for forces, a pull that is due to a rope, right? Then it's called tension, okay? There will also be gravity and reaction or normal force. If you're on Earth, you can either imagine this is in space or just out in outer space, or that just the fact that these two cancel, the box is not moving up or down. So let's just focus on the horizontal motion. Okay, and for a common mistake, can you guess what is the common mistake other than it's clear that it's connected to tension? Right, that's right. So a lot of people would go, oh, if I'm pulling here, so I must have an extra pulling force. No, A does not know of this pulling force. The pulling force is tugging on B. B is tugging on A. Okay. Now, however, immediately, if you've done this between the videos, did you differentiate these two T's? Do you draw it as the same T or the separate T? If you wrote it as the same T, why? Can you answer that? Now, if you cannot answer why, you need to distinguish them. All right, so I'm going to put a prime over there because this is a general rule in this class, and also it will serve you well for the rest of physics courses and everything in math, unless you have a good reason why the two variables are the same, and that reason is solid enough that it holds up under interrogation, and so you can provide a solid justification of why they're the same. If you don't have a good reason, make sure they're different, because it's more likely they're different. All right, until you're convinced that they're the same, then good, then use the same variable. Okay, all right, so we'll think about that. Just to complete the picture also, because I really, at some point, I need to relate this T to this T. Why do I even have to relate? Let's actually move forward and see what will happen if we forget to draw the free body diagram of the rope. All right, so I want to analyze the acceleration, right? So from the free body diagram of A, I'm going to write ma equals to F net. And the next thing is, well, because I'm going to write another equation for this as well, a Newton's second law for this guy as well. Now, is this m the same as this m? No, right? So let's give it an acceleration, a name. And the acceleration, is this a the same as this a? If you're not sure, put a different symbol first. And so apply A on everything, right? So this is the mass of A, the acceleration of A. So if I put A everywhere, that's definitely right. No chance it's wrong. Now, how about acceleration? I think I can now skip ahead and claim that the acceleration of A and B is the same. Because if A goes faster, accelerates faster than B, then at some point A will start to catch up with it, which does not make sense. And if it's slower, that means B is accelerating faster, but then the rope has to extend, but it's inextensible. So the fact that this is inextensible is important. That's why it is included usually in any problems, right? If it's not usually, if they don't even write it explicitly, you can assume this is the case, I think, for almost all of 3A. And then if it's extendable, that's the task, that's the duty of 3C. You'll see what happens then. And actually in physics, we call those springs. So anything that extend, I know there's rubber ropes that can actually extend, but we'll just call them springs because they behave the same way. Anyway, so for ropes or strings, whenever you see the word string or rope, we assume it's inextensible. So the acceleration must be the same. All right. So if you have a good reason for it, if you're convinced they're the same, you can just put A. I'm actually going to keep it like this. I want to emphasize the fact that you're just labeling everywhere. In the next step, when I plug in the numbers, I'm going to just call that A. And just for completeness, I'll write that here in case the grader does not know what I'm doing. Okay. Now let's write down the net. What's the next step? You write down the net force of A, which is just T. And that's done, right? I'm going to call this way positive X. Okay, that's fine. Or I can just put a brackets and say I'm considering it's T amount of newtons to the right, and this one is going to be what, P minus T prime. Okay, now I can plug in numbers, right? P is 10, T prime is, I don't know, T, I don't know. MB is 2, right? And AB is, A of B is just A. Over here, I have 3A equals to T. Can I solve this? How many unknowns and how many equations do I have? I have 2 equations and 1, 2, 3. 3 unknowns. I can't. Now, I have T and T prime. Are they the same? That's the question, right? That's the million-dollar question. Is this the same? And can you think of why? The reason has to be, you need to draw the free body diagram, and it's more subtle than you think. All right, a lot of books and notes don't actually make this clear. So be sure you understand why they are the same. And here's the reasoning. So let's draw the free body diagram of this guy. How do you draw it? Well, let's draw the physical diagram first. Physically, it's in contact with these 2 points, right? So this point, the box is dragging it this way. At this point, the box A is dragging it this way. That's the physical diagram, right? So this is so the box B is causing a tension on here. So this is the tension on the rope by B. And there's a tension on the rope by A this way. So, but we need to draw everything from the center of mass. So we'll draw what the rope feels, right? It feels a tension this way and a tension this way. Now, I don't want to put double primes and triple primes. That's going a bit overboard. So since I have potentially all different T's, let's label them. This is T1, T2, T3, T4, okay? But more precisely, let's add some explanation. This is the force on B by the rope, okay? This is the force on the rope by B. This is the force on A by the rope. And this is the force, you can fill in the blanks, right? On what by what? It's on the rope by A. Okay. Now, what is my goal? My goal is to figure out if T is the same as T prime. But now I've introduced more complications to the problem. All right, but fear not, let's think about it, right? Immediately you realize, hey, on A by rope, on rope by A, what does that mean? That's a Newton third law pair, right? You've just switched the object and subject. That means these 2 are equal. Yeah, let's circle them. These 2 are equal. T1 is the same as T2, okay? I'm putting brackets just sort of to emphasize it. There's nothing important. And I sometimes when I write T1, students think that, is there something special about a subscript 1? Does that mean it's on 1 by 2 or whatever? No, I just want to clarify. I just want to distinguish it from any jargons. All right, so this is equal, all right? Because of Newton's third law, you're just switching the object and subject. Same thing over here. So T prime, or I should say T3 and T4 are the same, again, because you're switching the object and subject. All right, good. Now I want to, so now the million-dollar question is, well, is T2 the same as T3? What's the answer? If you say Newton's third law, that is not correct, because this is not a Newton third law pair. A lot of even textbooks make this mistake. Newton's third law say if on something by something, you switch it, it's the same, equal and opposite. Now, spoiler alert, these are the same, but it's not because of third law. Look at this. This is on rope by A, on rope by B. This is not the swap of this. So this is not by third law. Well, what else do we have other than third law? Like I said, spoiler alert, they are the same, but why? The only other thing we've learned is with forces is second law. Well, let's give that a try. Let's write down Newton's second law. Let's write down Newton's second law for the rope. Well, that is MA equals F net, but guess what? This time we're gonna put rope rope. Okay, well, what's the net force of the rope? Net force is T3 minus T2, right? Towards the right, if I get a negative number, that means it's gonna be to the left. So I'm gonna define my positive way that way, right? So it's plus T3 minus T2 that way, okay? Now, these two would equal if this side is 0, right? What is the acceleration of the rope? Does the rope accelerate? Yes, of course it does, right? Because if I pull on this system, you can think of this whole thing as a 5 kilogram and just pull, it will accelerate, right? This is massless, so you can look at it as a whole system, like we did in example 1 in the very beginning, right? So the rope will accelerate together. In fact, the acceleration of the rope is the same as the acceleration of A and as the whole thing. Otherwise, if the rope is accelerating either faster or slower, it will either go beyond it or go backward, which either way doesn't make sense. So this is not 0. However, the mass of the rope is 0. So notice how important it is that I actually wrote down these two criteria, and all of the problems you will see in 3A, almost all of them will deal with massless ropes that are inextensible. Now notice, if I do have a mass of the rope, these two do not equal. Let me repeat that. If the rope is not massless, T3 does not equals to T2, hence T prime does not equals to T. These two T's are not equal, and they're only equal because I'm taking an approximation that this is extremely, extremely light compared to 3 and 2 kilograms. Maybe this is 1 gram, right? If it's 1 gram, it's 1,000 times, in fact, 2,000 and 3,000 times lighter than everything else. So it's going to affect like only 3 decimal places. If I'm only measuring things up to an accuracy of 1 or 2 decimal places or 2 significant figures, it's not going to change anything accurately. Now, if you want to be accurate, then add the mass of the rope over here. Let's say if the rope is 1 gram, you'd go change that to kilograms, so 0.001. The acceleration of the rope is the same over there. Now you can say T3, right? T3 is the same as T prime, and T2 is the same as T1, right? So T prime, I should say. So you have 0.001. Look, now you have 3 unknowns, but 3 equations, and now you can solve it. So now I've taught you not only how to solve these problems if the rope is massless, but also if the rope is massive. You add the mass of the rope over there, okay? Now, we'll focus on a case. I think there might be some 3-star problems in your textbook that actually have a massive rope, or it's just a non-massless rope. But most of the time, we will be dealing with massless ropes. So this is going to be 0. So it's not because, let me emphasize one more time, it's not because A is 0, it's because M is 0. And this is 0, which means T is equals to T prime. Now let me emphasize this one more time because it's so important. There's 4 T's involved. Force, the tension on A by the rope, the tension on the rope by A. These are the same because of third law. The force on the rope by B, right, because of this contact point, and the force on B by the rope is the same by third law. But the force on the rope by A and the force on the rope by B, so is the same, these equal because of second law. So many textbooks make the mistake and say that this, I forgot what exactly our textbooks say, but many, I've seen many times they would say, oh, it's because of third law that this equals to this. No, this equals to this not because of third law. It's the key bit, the essential bit is because of second law, okay? Actually, well, they're not all wrong. There's also, I guess, 2 to 1, 3 third law wins, but it's not how it works, right? Okay, yeah, so understand these two are equal by third law. These two are equals by second law. These two are, and the second law, the fact that the rope is massless, these two are equals by the third law. Right, so now, assuming that we are solving for the case where it is massless, all right? So we can actually just set these to be equal, all right? So I will just go and erase this. assuming that when I'm plugging in the numbers over here, I've plugged in t prime equals to t as well. You stare at this, and this is almost again begging you to just add up the two equations because there's t and minus t, right? If you want to solve for a, you can do substitution, whatever, but the easiest just add it up. So the left-hand side, you can add up the left and the right independently, they should equal. This is 5a equals to t, add that, it's 10. And of course, we get the same conclusion because if you analyze the whole thing as a system, it's the same as before, but this is the analysis, right? So if this is really the essence of Newton's third law. If you can understand this, you've mastered Newton's third law. All right.